Okay, guys, thank you all for being here tonight. I'm really pleased to see some old faces, but also new faces, people I've never seen before. This will be our fourth meetup, talking about blockchain. And so the agenda for the event is as follows. First part, we'll speak about notable news. I mean, some updates, what happened in the blockchain sphere, mostly developer updates. And second part, our guest lecturer, Preslav, will be speaking about assembly, introduction to assembly in Solidity, right? And third part, we just networking, asking questions, whatever, wherever you have. There are more people coming. Please welcome. We just started. So maybe first of all, who I am, because maybe you've seen before in other events, you've seen my colleague and friend Milen, who is mostly leading this event. So I'm not sure whether I'm online here. Okay, I try to fit. So my name is Christo, and I'm a business developer in Hack. And yeah, pretty much that's it for me. So let's move on to what is this part with the news. There are a few news that I selected during the whole month. There's nothing to do with my preferences, it's how the news appeared, so I selected them. And first we'll see something about Cardano, how they implemented some API, and it's very brief, I won't go into any details. We'll see another sidechain of Bitcoin, people trying to go a little bit more using Bitcoin as a sidechain and securing their transactions. Third, maybe you've heard, maybe you didn't. On the last event, we were speaking how Ethereum is going to implement Constantinople, but actually they kind of failed on the on their testnet, so they decide to postpone it. We'll see, maybe we say something about why. I found one news that I find it's interesting because most of you maybe work already with crypto, and it's very important, the security in this topic. So let's say I found this half of all exchanges are having security vulnerabilities and problems. We'll find what. Zcash is moving to sapling. They actually normally activated on the 29th of October. Bitcoin smart contracts, again, this RSK, nothing new, maybe most of you know. And the last one, some report really worrying for the big fans of EOS about EOS in general, like how it goes. So first, yeah, let's start with Cardano. They launched some project that is a toolkit API that is allowing new developers to penetrate Cardano network. I copy pasted things, but of course it's just letting you know, guys, what is going on, and if you're interested how this thing works, you can go and check for yourself. They implemented it already in the command line. So what is good for them and for the people that want to work with it, it will be compatible with iOS, web, and Android. So this is innovation for them. They sound maybe more technical people can answer, but could be considered. They sound pretty happy about it, so I guess it's a big deal for them. So there's Liquid. It's sidechain of Bitcoin. We already heard about Lightning Network for sure. I mean, this has been on developing for some time. Liquid, so what's the difference? Let's say that they are targeting more the big exchanges and big money movers, as Lightning Network is supposed to be working on micropayments and things like this. They will be implementing their own token that will be kind of redeemable for Bitcoin, which makes it very easy to transact with. This is something they sound also pretty happy about. So the main purpose of the technology is faster settlements, improved transactions, confidentiality, and actually you can tokenize a little bit with this. Interesting. Okay. The hard fork that Ethereum was planning and actually didn't really work very well for them, because they planned to execute on certain block time, but because of reduction of the block size actually occurred earlier, and there was a problem with conflict between the parts, between party get and another consensus problem. Afterwards they explained, and miners were not ready, and in general it just crashed. It gets stuck on testnet for some time. It was not showing anything, so they said, okay, let's leave it like this and we'll try to fix it till New Year's Eve. But on DevCon, few weeks later, or few days later, Vitalik announced that Ethereum 2.0 is really close, and they're really excited to show to the world what is coming next. So here we are. This is the one that with most numbers and things, but let's say that from one study of 100 most notable exchanges, or exchanges that have over 1 million of transactions per day, not transactions, I'm speaking bullshit, over $1 million of dollars, yeah, the value transactions per day. They pick up all those exchanges and they try to see what are their how they implement some proper security, and they found out that 46% of those exchanges actually are not meeting desired security parameters. Blockchain developers Meetup. Yes, please welcome. And so what were the problems actually? How they define those desirable parameters? Very interesting for developers, I believe, and really also scary. 32% of all exchanges, I mean, of those super exchanges had code errors that lead to operational malfunctioning. And actually, since 2010, I believe $1.3 billion were hacked using any of those like ways. User account security, 41% only. They ask for passwords longer than eight characters. They also some of them, maybe around 30%, allow you to make a password that is not alphanumeric, which means they don't have to, the user doesn't have to use numbers and letters, but only numbers or only letters, which also supposedly is like a security issue. They were also having some smaller percentages of other things, but yeah. And they have problems with the I don't know, only 10%, yeah, were implementing the 5 security measures that HTTPS, and as you can see the others they are just not. On top of the list come Coinbase Pro. There's no advertisement, and Kraken is the next one. The others, I don't know which were the worst performers. Usually wanna pick up the good ones if you want to trade. Something also very interesting, Zcash. It's pushing for this hard fork. Very, for me, yeah, very interesting solution they have. Really well told. I describe only one small part of it. With this hard fork, they will finally be able to, I mean, they now the shielded transactions could be used on light client, and this was a big problem before because even exchanges couldn't implement this functionality, let's say, because it was too much computation for the exchanges and all others. And now with Sapling protocol, we'll have 100 times less memory, which is still 40 megabytes, but it's a big improvement. And also we will have six or more times faster transactions. Slowly they were trying to move into privacy by default. They are implementing really the whole thing. They implement in a really cool way. Some people might not like how it is actually going to happen, because if you want to move from the previous version Sprout to this one, you have to actually show your identity, your address, you reveal what you actually, the amount of tokens that you actually own. And they say that because the Sprouts in the beginning was receiving criticism that if it's hacked, you would never know, because of this shielded transactions, you'll never know whether somebody is not printing money, and now they're going to try to show to the world that actually they control the situation. So yeah, this was about Zcash. And another solution about smarter Bitcoin, they were, because they use RSK, they were, this is the RSK, they are actually branding themselves or showing to the world that they're trying to develop a solution to use Bitcoin, and they're becoming like a side chain, yeah, I believe. And first in the world, smart contract that was using RSK on Bitcoin was used in this month, like some shipment company, they just simple contract is scrolled by the smart contract and integrate the RSK platform. Yeah, when the goods were received, the smart contract just unlocked the whole thing. It's interesting to see that companies are choosing to work on Bitcoin and to update and upgrade its scalability. The Liquid network, they were addressing the issue that I presented earlier. They're addressing the issue about the worries about the people with the centralization. They say certainly we will never be decentralized as Bitcoin, but we guarantee we cannot control. I mean, this is, we guarantee, yeah, but somehow they prove to the public that they don't control. And last but not the least, one of the big projects that maybe you all know, it's very controversial. Claim, actually the title was even that EOS is misleading the users, because they claim that they can have up to 1,200 transactions per second, which is incredible for what the blockchain can do. And actually it turns out it's not really the case by this company, this organization or company that was appointed to make a report on them. And their conclusion was that EOS actually, they're not sure whether you can consider EOS as a blockchain. Like they say it's some distributed homogeneous database management system. And they say when they try to test it, so EOS could reach up to 250 transactions per second in optimal conditions, which means no latency in the network and also no lost packages. But when they tested with like maybe standard at 50 milliseconds latency and also 0.001% of lost packages, then they realized that it's going to 50 transactions per second. So in optimal conditions, in real life conditions, this is how it works. They were also discussing maybe that, let's say, could be used as a side chain, but maybe it's even not as good protocol to be used as a side chain. So this is my thoughts. Normally we have, yeah, if somebody have something to say about EOS, maybe we can speak later about it. And yeah, that's it. I'm having all the resources here to see where this information comes from. Maybe for you it's just blah blah, you want to check it. And I'm leaving the stage to, yeah, please welcome.
I'd follow up. Okay, so that's about how you implement a loop. Now, another thing I want to show you how you implement an if-else statement in assembly. How do you do it here? Well, again, we can start by writing comments about what we want to achieve. So we say if num1 is greater than num2, then go to num1 greater. Of course, this should be kind of assembly and Solidity mix. It's a bit more difficult. Else something else, and now you have result is equal to num1, and then you have result is equal to num2. Okay, that's what we want to achieve. How do you write it now? Well, if you want to achieve if-else statements, you have to use jumps again. You have to use go-tos. And how do you write now? Sorry, is there something someone didn't understand I can explain again? Or go through an example. Would you like to, for example, go to a debugger and see how this executes? Anyone interested in that? Okay, cool. In that case, I will take this transaction and try to debug it. Okay, so we start executing this, and let's see what happens. We have a variable called I, which is somewhere here. Can anyone guess where this is? I can't, to be honest. That's why, to make things easier, I will cheat a bit and first stop the debugger and write the variable here so that I can track it in my debugger. Okay, so deploying my contract again, assembly loop, debugging. Okay, so now we can track what's the value of I here and the value of result. And let's see what happens now. So first we execute result is equal to result plus I. Okay, that's what we're trying to do here. We do that, and 0 plus 0 is equal to 0 when we execute the whole line, and this is the result. Nothing changed. Then you have I is incrementing by itself once, and I changed here. We can see in the watch. And finally, what we do is we say if I is less than 10, this LT returns 1 or 0. 1 means true, 0 means false. If that is true, then I want you to go to this label. Okay? So I execute this line of code, and what happens is we jump to the label again. What we have now, I is equal to 1, result is equal to 0. So we execute again, we add result with itself and I, and we get 1 as a result. Okay, so what we basically did is result plus I, which is the same as result is equal to 0 plus 1, gave us an answer 1. We increment I again, and we got 2 as a result. Now we check if 2 is less than 10, which is the case, and we again jump to our start of our loop. Now we add result to I again, we get 3, and this thing repeats. So we do it again multiple times, and as you see, what we get is this, that this looks different than a for cycle, but it implements the same thing. It still implements a for loop without using the keyword. And we implemented it only using a conditional jump. Okay, so I will fast forward a bit to see what happens in the end. I'll have to fast forward a lot since... Damn, you're very proficient at this. Okay, 9. Okay, finally we got a result of 45. We add 1 to I and we get 10 as a result. And finally what we do is we check if 10 is less than 10, which is not true. Therefore this jump won't execute. What we'll do now is we directly just leave this function, and we do that, and that's when our function ends. We move to the next line, which is here, and we don't have a label here or any other instructions. That's why our function ends. Okay, that's how you implement a for loop in assembly. Okay, any questions? Yeah. That's interesting. So what Nicola asked is, when I declare in assembly a variable, I use let. That's uint. How do you declare other data types? Well, the thing is, if you want to, let's say, declare uint of 32 bits, what you have to do is you have to declare it as a normal uint and then do bitwise operations to make it 32 bits. So essentially you say, I want to declare a 256-bit number. For simplicity, let's say it's 8 bits. 1101 1001. That's our number in bits. So that's a uint. uint. Normally in assembly, in Solidity, it's 256 bits, but of course I don't have enough space to write it all. So assume we have 8 bits. Let's say we want to change this to 4 bits. So we have 8 bits, change to 4. How do we do that? Well, what we can do is we can take a number which is 0, 0, 0, 0, 1, 1, 1, apply an AND operator, and we get 1, 0, 0, 1, 0, 0, 0, 0. Anyone knows bitwise operations? Okay, awesome. So what this does is it says go through each bit of the number and apply the AND operator. The AND operator says if you have the bit 1, 1, you get 1 as a result, but if you have anything else, you get 0. That's you already know from logical operators, but this time you just apply it on bitwise operations. And what you do here is, instead of having 2 Boolean variables, you go through every bit and you execute it for every bit accordingly. So you say, hey, I have 1, 1, the result is 1. I record it here. Then I have 0, 1, the result is 0. I record it. 0, 1, the result is 0. 1, 1, on and on and on. And the thing is, with this operation I did just now, essentially what I say is I want to take only the first 4 bits of the number. That's how I would take an 8-bit number and translate it to a 4-bit number. And if you want in assembly, in Solidity, to do the same thing, to have a uint 256-bit and make it a smaller data type, you would have to do essentially similar operations. And you might say, okay, that means assembly sucks. Why should I do that, since I can do the same thing in normal Solidity? Yes, you can do that. So you can say in normal Solidity uint 32, and that will work flawlessly. But under the hoods, normal Solidity will do the same thing. Whether you do it explicitly in assembly or you do it just by declaring uint 32 in normal Solidity, you will still get these bitwise operations which make the bigger data type smaller. Okay? Yes? Okay, so what the colleague asked is, what's more gas efficient, to use uint 256 or uint 32, essentially? And what you mentioned is that you can save space with uint 32, right? The thing is that in Solidity you actually don't, because here I showed you that when you have an 8-bit number and you want to change it to 4 bits, you apply some operations to make this number here. It looks like a 4-bit number, but in reality it's 8-bit. And in Solidity, if you have a 32-bit number, it will look like a 32-bit number, but it will actually be a 256-bit number. Which means that if you use uint 256 or uint 32, it will take the same amount of storage. There's a special case to that. I'll tell you that soon. But in normal case, it uses the same amount of storage. And what's more, using a uint 32 is more expensive. Because when you use a uint 32, you have to apply more operations to make it a 32-bit number. You don't have a 32-bit number out of the box. Okay? No, you have different. Yes, essentially under the hood, everything's one data type. It's 256-bit number. But the way that data type is interpreted makes other data types, let's say strings, characters, structures, and things like that. And even Booleans are 256-bit, yeah. And in this might sound strange to you, but in normal programming languages, like, well, okay, Solidity is a normal programming language. in other programming languages like Java, PHP, C#, and others, it works the same way. In Java and C#, you still have, everything is still a 64-bit number, or a 32-bit number. I'm not very, I don't know the specifics there, but the thing is you still have only integers. But these integers get interpreted in a different way to achieve different data types, like strings, characters, persons, people, and whatnot. Okay? The same way, so if you want to achieve a data type called person in C#, you would say person which has string and int. Okay? You say this is a person. You know that under the hood this uses a string and an int. When you have these primitive data types, you would still you still have this thing, but it's implemented under the hood. Okay? So that's one cool thing. That's one nice takeaway from Solidity assembly, right? That actually everything is an integer. Okay, and any other questions thus far? Okay, awesome. So let me just scroll here to our live demo and go forward. Now the next thing we have to implement is an if statement. What we have is a function called normal if, which says which number is greater. If the first number is greater than the second, the result is assigned that number. Else you get the other number assigned. That's everything. How do we implement that in Solidity? Well, we can write this, since it's more easier. We can say result is equal to num1 and result is equal to num2. So this was the easy part. Now how do we do the more hard part? Well, in this scenario here, we actually have different code paths which can get executed. You can't execute both. You can't execute both this line and this line. And we have to implement the same thing in assembly. In order to do that, we first have to label our sections of code. And the way we do that is we assign labels again. And here the label would be num1 is greater. And here the label would be num2 is greater or equal. Just to identify what's going on. Okay. Well, this should be here. Okay, cool. So we have this thus far when we have two labels and two instructions. Now, how do we achieve an if statement? Well, again, we can use a conditional jump. A conditional jump, just to remind you, says if this condition is met, go to that label. And what I can do is I can say I want to go to the label that num1 is greater if the first number is greater than the second one. GT stands for greater. This line here is the same as writing num1 greater than num2. And I say, look, if this is greater, then go to num1 is greater. Else, I write an unconditional jump, which means in every other case, I want to go to the num2 is greater or equal. And let's see what happens now. I'll actually leave you a hint here because this is not totally complete. But essentially what we have is if the first number is greater, go to this label. If the second number is greater, go to this one. Okay. And now let's deploy and see what happens. So I say 5, 2. We get 2 as a result, which is incorrect. But if we write 2, 5, everything is okay. Okay. Now let's see what happens. I will go through the transaction with the debugger. Actually, I want to debug the other one, the faulty one, like this. Okay. Debug. Okay, I start running this example here, and I say if the first number is greater than the second one, jump to this label. I execute this, and this is correct, so this condition returned true. So we go to that label here, and we execute it, and we say result is equal to num1, and you get it here. Let's see what goes wrong now. If we continue executing this code, since we don't have any jump instruction here, we just continue executing the code line by line. The next line is this one. So we continue and we actually go to the second case, which is that num2 is greater or equal. We execute it, and now the result changes to 2, which is not the correct result. Okay, now knowing this, can anyone tell me how can we fix this? Yes. Yep, awesome. Okay, so that's totally correct. Thanks, Yule. As you saw, when we got to this line here, when it executed, we continued executing these lines here. In order to avoid that, we have to do another jump, which says, I don't want you to continue executing this. I want you to go to executing this part. Okay, and now if we execute this transaction, first I have to deploy, of course, 5,2, we'll get the correct result. So we get a result of 5. Let's see what happens this time. Okay, so we do the same thing. We go to this label here, and this time we get this jump here, which means I don't care what comes next. I don't care about any conditions. I just want you to go to this line. So we execute it and we get to the end. And that's how our function this time executes correctly. And if you're actually more if you pay attention to how a debugger executes these lines of code, you see that it does essentially the same things. For example, if it gets to this part and it executes it, it won't continue executing this part. It will directly make a jump and go to the end of the function. So that's how you create if-else statements in assembly, again with jumps. And basically these are the two most essential constructs you need to understand how to create most programs in assembly. Are there any questions thus far? Questions? Okay, awesome. Well then, I will continue, and here I'll show you something very fancy. Now what you saw thus far was that this was what do you think about this code we saw? What do you think about assembly? Sorry? It's cool, right? Yeah, it is cool. Actually, it's really fun. But what if I tell you that what we just saw wasn't real assembly? It was something which is very close to assembly. It has the same principle, but it's not actual assembly for the EVM, because the actual assembly is more, well, strange. This is a simplified version which allows you to write assembly code and kind of understand it. Now I will show you a version of assembly which is totally unreadable. In this version, if you like this one, the next one you totally hate. Or if you like very strange things and hardcore things, maybe you would love it even more. This is called instructional assembly. Thus far we saw functional assembly. This is something which resembles high-level languages, but instructional assembly is something which resembles how opcodes are executed in the EVM. And let's see what it looks like. Be warned, the next lines of code, when you see them, perhaps you get a headache or you might get dizzy, because it looks very I even can't explain it. It looks pretty cool. So this is instructional assembly. I will zoom in so that you can see everything. Okay, so this is a normal loop we saw previously. It's basically the same thing we just wrote. Okay? And I'm using this low-level assembly to demonstrate how the even lower level assembly works. Okay, so that's what I have to do here. And let's see how it works. This is instructional assembly. Anyone understands what's going on? Yeah, awesome. Well, the thing is that this now actually executes with a stack. The virtual machine, I told you, is stack based. This means that in the virtual machine you have a stack where your variables go to. And in that stack, you execute some things, and basically you implement anything you want. I will explain it. The way a virtual machine works is you have a stack, and let's say you have two numbers. So you have 1, 2, add. The way a stack works is it gets to this line here, and it pushes 1 to the stack. It goes to this line here, and it pushes 2 to the stack. Thus far, nothing interesting. But when it gets to add, what you do is you remove the two topmost variables from the stack, you add them together, and you add the result on top of it again. And when you have another instructions, you do the same thing. The different instructions take different parameters, but the thing is that this time you don't just have a list of variables available in the function scope. You have these same variables ordered in a stack. And you have to operate with the stack, not directly use, the variables just like you use in normal programming languages. And let's see how it works now. So in order to parse this code for you, I will have to first copy it and explain it line by line. Cool. I'll have to drop the screen even more to be able to copy everything. Okay, cool. So I'll actually explain only part of it because this is really insane. I'll paste it here. Okay, so what we have is this lovely code here, which is ununderstandable. And we have our stack. So our virtual machine has a stack in it, and it starts executing the code line by line. What it does is first it goes to this line here. It says 0. Okay, this means that we push 0 to the stack. Before that, I have to mention that you have another variable there, 0, and this variable corresponds to our variable called result we previously saw. This variable 0 corresponds to I. This is our counter. Okay? This is just to label the numbers we have in the stack so that you can understand them. Then we say, okay, go to this line here and duplicate the second variable from the stack. This means take this number and push it on top of the stack without deleting the previous one. That's what duplicate means. So this is essentially duplicated version of result. Then you get duplicate 2 again, but this time you don't get result since its index changed in the stack. You get I, and this gets pushed here, and this is the duplicated version of I. Then you perform the instruction called add. I have to clean up this a bit, which says take these two numbers, add them together, and push the result on top of the stack. So this gets deleted. Finally, I want you to take this, which is the result. So this is result plus I, and I want you to swap it with the second number in the stack. So the second number is this. I want you to swap these two numbers, which means that I delete this 0 and exchange it here. Of course, here we work with zeros, but if it was something else, let's say here you had result, swapping the two numbers means delete this one and assign 5, and here you assign 0. And that's how you execute adding two numbers together. Okay, and finally, since we don't need this 0 anymore, we execute an instruction called pop, which means remove the topmost number from our stack, which is this one. So we remove it like this, and we have our stack back to normal, and we continue executing the instructions again. So this is only a very brief overview of how stack-based instructions work, and I don't want to go through the entire code example because it will take some time. But essentially the takeaway from here is that when you have assembly in Solidity, you don't have this nice looking function syntax. In reality, you don't have this here, okay? You don't have this. This is just a simplification. In reality, you have this. This is something which actually, this is how EVM opcodes work. If you open real bytecode, compiled smart contracts, and you try to translate the numbers to the opcodes, you would actually see something like this. So I wanted to show you where this all comes from, but in reality, I hope you don't encounter this. If you do, please kill the person who did. But just to let you know, if someone tries to surprise you on Halloween, he would probably give you this code. So I'm preparing you not to be surprised now. Okay, so that's instructional assembly. Any questions? Yes. So yeah, the question is there any limit to the stack count? Yes, there is. And when the limit of the stack, when you reach the limit of the stack in C# and Java, let's say, you get a Stack Overflow exception. If you've written a recursive algorithm, perhaps you've encountered it. What has essentially happened is that this stack here reached its limit, which is something predefined, let's say 1000 bytes, for example. When you reach it, you get that exception. So in Solidity, you have that as well, but I haven't really seen the exception or the error. I would guess that you would get some, I don't know, revert or something else. But you still have it. You have it in any programming language. Sure. Okay. Sorry? Using this? So if you are very, very knowledgeable and you like delving into these details, it might be cheaper. But I would say that you can hardly get it cheaper than this, because although this is an abstraction, which means that it's a simplification, it still has almost direct mapping. So the thing is that the more high level you get, the bigger performance loss you get. The more low level you are, the less performance gains you, the more performance gains you get. And this is low enough. There is no need to go even lower. I haven't tested it, but I would say that normally you wouldn't need to use that. Simply, the reason for this is that if you have normal, let's say, for loop, it is hard to translate this to this for a compiler, to translate it efficiently, okay? But if you get this, it's easier to translate it to the most efficient version, okay? So I would say probably no. But of course, everything which is concerned with performance, normally the answer is test. Anyone which talks about performance would say you have this nice tweak here with which you can boost your performance, but you have to test if it works. And even for some very controversial techniques, you still have to test. So in this case, I would say the same thing. Okay? Sorry? Okay. Yeah, you're right. That would be best. Cool. So instructional assembly. Okay, we get the same thing, and now let's see in terms of gas cost what it looks like. Well, I forgot which was which. Okay, assembly loop. This is the higher level assembly, is 700 gas. Instructional assembly is 651. Yeah, okay, it got even more efficient, but not hugely. Okay, cool. So, anything else? Okay, awesome. Then let us move forward. So the next thing is memory. That's cool. Well, now we'll delve into a bit more Solidity details. Thus far, you've seen something which is generic for any kind of assembly language. Here we have something more Solidity specific, like the different memory types. First, you have stack memory, which you've already seen. When you write instructional assembly and you write those numbers, you actually modify the stack memory. This is something which is available in the function scope. That is, every function has its own so-called stack frame. This is the portion of the stack which it can use, and you modify it. Apart from that, moving forward, you have memory. Memory is the same thing like dynamic memory in C++. Memory means that your variables are available throughout the whole contract call or throughout the whole execution of the program. So, as you know, in C#, let's say, if you write some variable in C# in your function and you try to use it in another function, you can't access it, right? The reason for that is that this variable is in the stack memory. But if you allocate it in the memory, it will be accessible. Now, in C# you don't have memory, but you have heap memory, and that's the same thing essentially. Then you have storage, which is something similar to persisting data on your hard disk. This means that you can open a file, write something to it, and when someone executes your program afterwards, he can access the data again. Finally, you have call data. This is totally Solidity specific. Call data is a special memory segment where you can find metadata about your transaction. For example, in the call data, you can find who is the sender of the message. You can read how much gas price you have. You can read, I don't know, what's the signature of the transaction, stuff like that. These kinds of things you don't have in C#, Java, or something else because they're not, you know, blockchain things related. But in Solidity you do. And that's totally blockchain specific, and we'll see how we can utilize that. So let's see an example. Now, first we won't go into working with stack memory because we already saw it. You just declare variables like normal. But you have memory, where you have these three instructions: mload, mstore, and msize. What this does is it takes some number and it loads the data you have at that address. This stores some data at a specific address, and msize, basically you can see what's the current space your memory is taking. And here I'll show you a brief example because I won't want to get into too much details here. And we have an example of code where you have an array and you calculate the sum of it. You calculate what's the sum of the array. Let's see how it works. I will deploy this contract, and you have normal sum of array 1, 2, 3, 4, 5. Okay, this, yeah, it should be an array like this. Executed, I get 15. Okay, that's what I want to achieve. Now in assembly this will look a bit more strange. An array is stored in the following way. You have normally your elements. So let's say 1, 2, 3, 4. That's what we've all learned. That's how an array is represented. That's how we work with it. But in reality, you have some other data. And that data first is the length of the array. In this case, it will be 4. So before you access your elements at the first slot, you have what the length of this array is. Okay? And in Solidity, that's how an array is stored, which means that if you want to access the first element, you don't get the address of the array, you get the address of the array plus 1. But if you want to get the length, you get that specific address, and I'll show it now. So if you want to get the length of this array, you just load what's at the array address. But if you want to get the address of the first element, you get the address of the array and add 1 to it. Now this is a very strange one, and the reason it is 0x20 is because 0x20 is the same as 256, and we use 256 because in our memory every element is 256-bit long. So if we want to get the next element, we get what is after 256 bits. Okay. Actually, 0x20 is 32, which is 32 bytes. And 32 bytes is equal to 256. Yeah. Yes. Okay. So we get the element address and we have some counter. Now, I won't go into too much details in this code, but basically, essentially what you do is you have a variable called sum. We already saw that. We add sum. So we write sum plus whatever is at the current address of our element. So we get the current element, which is array of I, let's say. And then we increment the current address. Now, this is very similar if someone's written in C++. This is very similar in like iterating an array with a pointer. So if you write this code in C++, you will do pointer arithmetic. In Solidity assembly, you have to do essentially the same thing, where you get the address and you say every time add 32 bytes to it to get the next element. So I'll just walk through an example how this works. So you have the element address here, and we have sum is equal to sum plus the current element. We add it, then we move to the next one, the next one, the next one until the end. Essentially, that's what we're doing here. And I don't want to go into too much details. If anyone's interested in using memory, you can read more about it. And apart from that, I will give you the code examples as well. And the next example is a bit more involved, as you can see. You can go through it. It's fun. If anyone's interested, he can stay after the seminar and we can go through it. I just won't go through it now because I don't want to take too much time. Okay, cool. That's about memory. We saw the live demo. Then you have storage. Now the thing about storage is that it's stored in something called the Merkle-Patricia tree. I know this sounds very hard and very strange and unknown. Don't worry, you don't have to know what this is. Basically, it's a data structure, which is some kind of tree. The takeaway here is that when you have storage, you don't have some array in memory you use. If you have normal memory, you can imagine it as an array of bytes, and you can access any byte you want in it. But if you have storage, it's not a normal array of bytes. You have something a bit more something a bit stranger. That's why you have, when you want to access any kind of element, you have some special variables out of the box. For example, if you have a variable called x in storage, you would have these you would have these variables which are there. You don't have to declare them. You just have them. It's hard coded, and you can use them to load something from storage and store something in it. And I'll show you a very simple example of having two variables with two functions which is for setting them and one function for swapping them. How does it work? Well, if you want to store something, you have this variable x, and you get x slot plus x offset, and that's how you get the address in storage. You execute store and then you store some value. You do the same thing for y if you want to do the same thing. And if you want to load from them, you have sload. So you have sload of the address of x, sload of the address of y, and then you have normal stores like before. Okay? It's a bit more involved with these adds here, but you don't have to look through this code specifically, what it looks like. You can just interpret it as the address of x. If you're interested in how exactly to get it, you can always refer to this code example, but essentially you have some address. The thing is, you don't directly access it like in memory, let's say, but you use some other special, instructions. Okay. Anything about storage? And finally, we have call data. This is something Solidity specific, where you have read-only memory for storing the transaction data. For example, if you want to read who the message sender is, what the function signature is, stuff like that, you have to access this memory. And what's more interesting and something which can be useful is that if you have public functions, this memory, entire memory segment, is copied into the normal Solidity memory. Which means that if you're passing, let's say, an array in as a parameter in a function, before you first work with it, you copy it to another place. Even if you never need that, you will still have to do that. But if you have an external function call, you don't do that. In external function calls, you don't copy the call data into memory. That means that essentially when you have an external function compared to a public function, even if you have the same code, the same instructions, everything the same, only the keyword different, external functions will be faster for large arrays of data. And I'll demonstrate that. Yeah, and yeah, cheaper. That's what's actually more important. So you have sum array public, which is this code here. It calculates the sum of an array. And you have sum array external, which is the same code. It's the same snippet of code. I haven't changed anything. The only thing which I have changed is this modifier, this keyword. And now, if I deploy this contract and I call sum array external, and so I pass some variables 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I just want to be big. That's what she said. You calculate it and you get 55. Okay, both work fine. Now let's see how they compare. First, we have the external function call, and it took me 1,700 gas. You have the public function call, which took me more with the same snippet of code. And for small arrays of data, of course, this is negligible. Well, it's not important. It's not a big performance gain, but if you're passing a very large array, using an external function can save you a lot of gas. But there's a drawback to this, and the drawback is that if you use an external function, you can't. So if you use an external function, you can't write to this to these parameters. Normally, if you have a public function, you can modify the array as normal. But if you have external, it is read-only. That's why in this function here, which I have commented, I'm doing the same code like before. You see the same snippet of code, but this time we get an error. This doesn't compile at all. And the reason it doesn't compile is that it gets some strange, error message. But essentially, what it means is that external functions, when you have external functions, you can't modify the function parameters. So that's the price you have to pay for using external function. But if you don't want to modify the function parameters, you can use it to save some gas. That's why in many smart contracts, production smart contracts, you will see that many functions have the external keyword instead of the public one. The reason is that they save some gas this way. So essentially, that's how the call data type works, and this is the end of my walkthrough of assembly in Solidity and how it works. What we cover today is that different languages differ in terms of how they're built, and this drastically affects their performance and the way they're used. JavaScript is way easier to write in than C++, and the reason is that not JavaScript creators are magicians. The reason is that it uses an interpreter and C++ uses direct compilation. And Solidity is a VM-based language. It uses a virtual machine. The reason it uses it is to achieve portability. You want to write one smart contract and be able to execute it in any environment. And if you write assembly in Solidity, you can achieve some optimizations, you can save some gas, and apart from that, you can achieve some missing language features. And finally, the final thing I want to mention is that mainly the reason I showed you all this about assembly is that in many production smart contracts, you will see assembly being used, and you might be frightened. You might say, oh shit, this is assembly. Time to go away. I want you to go now and understand that assembly is not so hard. Actually, assembly is way easier than using high-level languages in terms of the instructions you have. But normally people get frightened because they have never felt what it is like. And the goal of today's topic was to get you introduced to it so that you're not afraid. And if you have to use it someday, you now have the mindset and tools to your disposal to tackle whatever problem you face. So thank you a lot. And if you have any questions, this is the time to ask. Well, too little, too late. Няма звук, and there is no sound. Well, not something on the news. Okay, any other questions? Yeah. Yes, so normally I showed you only a subset of the whole opcodes you have, but you have opcodes like call and call data, which can be used to call external contracts. When you use normal assembly, you have them available as well in functions, so you have functions like that you can use, and you have some more high-level functions called transfer and send, which essentially do the same thing but specify some parameters. Normally you would see, okay, I won't get into that. People say that send and transfer are more safer than call and call data. But what you have to understand is that essentially send and transfer are the same as call and call data. It's just that they use a specific parameters which make it safe. In assembly, you don't have send and transfer. You only have call, and you can use it. It is at your disposal. It's just a bit more harder to use than normal assembly, simply because than normal Solidity. It's harder to use than normal Solidity, simply because it's assembly. But you do have them, and you can read about it in the documentation. Okay, yeah. Yeah, one specific. Greater performance. Yeah. Yeah. So one case I've seen, it's an actual smart contract which allows you to use string utilities. There's a contract which allows you to concatenate strings, search for substrings, and stuff like that. In Solidity, you either can't do that or it will be very costly. But with assembly, you can easily do that with, you know, some for loops, assembly for loops, of course. So that's one example I can actually show you. If you're interested in string utils Solidity, this actually uses assembly a lot. If I'm able to find a specific subset of contract, here you can, let's say, find this. This is assembly, and it's this contract, and it's a production contract. I'm not sure whether someone uses it, but it is quite popular. So that's one example where I've seen Solidity assembly being used. Another one is implementing something called a proxy contract, which is essentially proxy contract Solidity. Maybe this. Okay, yeah, this is it. So this is a proxy delegate design pattern where essentially what this guy is trying to do is he wants to say whenever someone calls some function in this smart contract, forward it to another. So let's say you call the function, you know, add x and y, and you don't have it in this smart contract. What you do is you forward that call to another contract which presumably has that function. And the way this design pattern is being used is that you have this address hard-coded here called delegate, which is an upgradable smart contract. And what you do is you have your smart contract, it's hard-coded, and if someone wants to use it, he doesn't directly call that, he calls this. It's just a router, it forwards the function call. And if at one point that smart contract is obsolete, you want to change it, all you do is change this address here, and it will work the same way. Flow seamlessly for the end user. Okay, cool. Anything else? Awesome, so maybe we can close this session now, and I'll stay a bit afterwards if anyone wants to ask any questions. For the rest, have a great evening, and thank you all for coming and staying this late.